Alright guys, in order to talk about gravitation, we need to have planets. Here's the moon, here's the Earth. Alright, so maybe the moon's not a planet, the moon's a moon, not a planet. Anyway, Newton's law of universal gravitation, this guy over here, says that any two objects with mass, moon and Earth definitely have mass, are attracted to each other along a line between their centres based on how big their masses are and how far apart they are. So there's going to be a force that way from the Earth is attracting the moon, so there's a force on the moon. But Newton's third law, so this is one of his, Newton's third law says that forces come in pairs, equal and opposite, so action-reaction pairs. So if there's a force of attraction on the moon, there's an equal and opposite one on the Earth. It holds. Newton's law of universal gravitation is also one of the big ideas with it is proportionality. All right, you'll notice that the term on the bottom is squared. So if I was to double one of these, what I would do is, so let's say I doubled the mass of the moon. Now that's definitely twice as big. All it means is that I'm going to double the size of these forces, and I didn't think this through at all. So what I'm going to do is, that would make these two forces twice as big, because I've doubled one of the masses. It makes this top line twice as big, the force must be twice as big. However, if I was to change the distance between them, I just worked out that I'm not going to make them closer, I'm going to make them further apart. So double the distance. Yeah, that's about right. If I make them double the distance, what I'm actually going to do is make them a quarter the size. Alright, now the trick with that one is, so I'm changing the distance, but if I'm doubling the whole distance, so that I'm doubling the distance, I'm not doubling the square, I'm doubling the distance. Now I'm ending up with two lots of r that's squared. Now I've got my original r still, but I've got a factor of 4 there. That factor of 4 is on the bottom line. So if I make the distance twice as big, I make the force 1 over 4 times the size. I make it a quarter. If I make the distance 3 times as big, it's going to be a ninth. Flip side, if I brought this closer, think of it a similar way with magnets. If you bring them closer together, the force of attraction is stronger. So if I was to halve the distance between here and the moon, magically, I'm Jim Carrey in that movie where he plays God for a bit. You guys will remind me. If I was able to bring the moon closer, you would end up with all of the tidal waves and Bruce Almighty. You would end up with all the tidal waves because the gravitational force, the forces from the moon would be 4 times the size. So you bring it half the distance away. So if I halve the bottom line, I'm squaring the halving. We're going to end up with 4 times bigger. If I bring it a tenth the distance away, it's going to be 100 times bigger. Alright, it's really important to get your head around. There's forces to do with charged particles that also have an inverse square law. That's important to kind of remember that squaring of the bottom line, because it is really important. Now, in order to have something that can orbit means uniform circular motion of some description, or some sort of uniform motion, and in order to have that we need a centripetal force, because that's going to provide a centripetal acceleration, and this must be at right angles and it must be also constant. Otherwise we can't actually have this centripetal force, can't actually have centripetal motion. Now the only way to do that is to have the centre of that orbit be the centre of Earth, for instance. So we can have orbits that go over the top. I'm getting used to drawing these. Over the top, that one there would be called a polar orbiting satellite, because you guessed it, it goes around the poles. And you can also have other ones deliberately bigger. To scale, it should be like 100 times bigger than that again. And these ones here are a special type, geostationary. You can also have equatorial orbiting satellites that have smaller orbits and stuff like that, but as long as their centre of their orbit is drawn better than that, as long as the centre of their orbit is around the centre of the Earth, then you can actually have that as an orbit, because it's going to be constant in size and always always directed towards the centre of the circle. So if I was to have an orbit, let's say around here, orbiting around Antarctica, Australia, New Zealand, whatever, here we might be able to say that it's at points perpendicular to the motion, but it's definitely not going to be constantly towards the centre of the circle, so it's not going to be causing uniform circular motion. It's got to be something else going on here. So that one, sorry, you don't exist. Alright, so the polar orbiting satellites, these ones are close. Geostationary ones, they're not that far, they're like 40,000 kilometres out. Geostationary means that it's above the same point on the Earth, so geo, Earth, stationary, not moving. So it's above the same point on the Earth all the time. The only place it can do that on Earth is in the direction that the Earth actually orbits itself, which is, has to be above the equator. In Australia, we're kind of lucky because you can stick an Austar satellite and point it at one of these things, a satellite internet satellite, and point it at one of these geostationary satellites, and your satellite dish doesn't have to move. It doesn't have to try and pick up 4 or 5 different satellites at all. It just picks up one, never has to move. If we were, say, really close to the poles, we may not have line of sight to it very well, or it's just a lot further out, so the internet's even slower, or Austar's even fuzzier or something or other. These ones are really good because they're always there. You've always got them. The other ones, the polar orbiting ones, because they're nice and close, you can actually get higher res photos because your camera is able to pick up more detail in whatever it's looking at on the ground. It's also able to monitor weather patterns a lot more consistently. So the geostationary ones can monitor what's kind of underneath them in this sort of band here. The polar orbiting ones are constantly doing laps every 45 minutes to an hour and a half or two, constantly doing laps, and there's banks and banks and banks, and there's heaps of these things, and it will be able to surveil, look at the same point on the Earth's surface lots of different times per minute, lots of different times an hour, or lots of different times a day, so you actually get reasonably updated stuff, pretty high resolution. In order to look at the speed of one of these satellites, I'll get to Kepler's stuff in a sec. If we look at the speed of something that's going in an orbit, so if we look at this, so satellite going in orbit has an orbital period t, it's got a radius of orbit r, all that sort of stuff. But we also know that F is mv squared on r. We also know that, so this is the centripetal force, we know that the force that's causing this satellite to actually stay in orbit is in fact Newton's law of universal gravitation. M2 here is the mass of the orbiting thing, well that's the way I'll put it, so I'm going to put M2 over here because that's the orbiting thing, and if you look kind of closely, what you can start to see is that the M's cancel out, or the mass of the object doing the orbiting cancels out because they're on both sides. So we end up with V squared on R is Gm on R squared. Hopefully you can spot one of those cancels out with one of those, and then you're left with V is square root of Gm on R, square root, get rid of the V squared bit. So now, there is a speed which is unique for each orbital distance from the centre of the Earth. So if it's 100 kilometres up, or 500, or 600, or 700, it doesn't matter, but the ones that are 100, and the ones that are 2, and 3, and 4, and whatever on however many kilometres up, every different orbital radius has its own unique speed. If you don't match these two things together really well, then your thing's not going to do uniform circular motion, and it may just come back down to Earth like some Chinese space station has done very recently. Now Kepler was doing a whole bunch of astronomy stuff, and this is what he came up with through observation. Now what we're going to do is try and get from this thing here, using this thing here, to that thing over there. So Kepler's talking about the orbital period of moon satellites things around the sun, so planets like us in our solar system, is related to all of this stuff. M is the mass of the thing at the centre, so our sun. R is how far away that planet actually is from it. So if we use, let's go blue, V is square root of Gm on R, and V is also 2 pi R on T. The ugly thing here is the square root, so let's get rid of it. Gm on R is 4 pi squared R squared on T squared. Now, Kepler's trying to get the T squared on its own, so if you can measure the time that it takes for something to do a lap, you can kind of work out how far away it is from an object, or if you know how long it takes and how far away it is from that object, you can work out the mass of the thing at the centre of it. Pretty handy if you're trying to work out how heavy new stars that we're looking at are. Therefore, T squared, that's what we want. T is on the bottom, we're going to swap it over to the top. Gm on the top, we're going to swap it down to the bottom. R on the bottom, that's going to go diagonally up. So let's take all those steps a little bit slower than what I just said then. So now we've got Gm and T squared swap spots. Gm on the bottom. The R goes up with the R squared, so we end up with R cubed, and the 4 pi squared go together. So now we know a whole bunch of stuff about orbiting planets. Kepler had 2 rules. He said that for everything that orbits another thing, so our Earth going around our Sun, so that's Sun, that's the Earth. The Earth goes in an elliptical orbit, we all know that. Ellipses have 2 foci, 2 sort of centres, I guess. One is where the sun lives, and the other one's probably there-ish. So that's one of his 2 laws. The other one is that it's over a certain amount of time, so let's say a day. If we were to draw a wedge here, and then the next day, and then the next day, and then the next day, and then go back in time, and blah blah blah. All of these wedges should be the same area. So as this thing's further away, so as the satellite is further away, as R gets big on the bottom line, V gets slow. So when the satellite's out here, the Earth is out here, it's moving reasonably slow through space. However, the wedge that it's drawing might be small, but it's really, really long. When it's a lot closer, R is a lot smaller on the bottom line, V is a lot bigger, therefore it might be sweeping through a larger wedge. It might seem like it's a larger angular-wise, but it's the same area. Okay, so those are his 2 things. These are really important so that you can map things in space, especially with our solar system. Alright, the 4 key ideas that I want you to get out of this one. Newton's law of universal gravitation provides a centripetal force for things in orbit. So satellites, moons, planets. We can have 2 different types of orbit for satellites on Earth. One, polar, they go north-south above the poles, and the other one is geostationary. You can also have equatorial ones, but we don't really talk about them too much. These ones are far out, they're a long way out, in the tens of thousands, 40-something thousand kilometres up. They're always in the same spot in the sky. It's like a big stick, 40-something thousand kilometre long stick with a satellite at the end of it. These ones here are a lot closer in. There's a lot more of them. We can use them for high-res and high-res imagery, so Google Earth, that sort of stuff, satellite photos, or for weather surveillance really quickly. We can also ignore the mass of that satellite other than when we're trying to launch it. So this M here is the mass of the Earth, this is its orbital radius, this is the speed that it's going at. So you could put a whiteboard marker in orbit, you could put me in orbit in a spacesuit, you could put a fully loaded B-double truck or a 10-kilometre long road train. All of these things, you could stick them in orbit, their mass is irrelevant. It takes a lot more effort to get me up into space than my whiteboard marker. However, once we're in orbit, same speed at the same radius. Kepler used this idea with things going around ellipses, so elliptical paths, Earth around the Sun, and could therefore use this thing here, Kepler's law. That's Kepler's law, derive Kepler's law based on the speed of a satellite in orbit and the speed of something going around a circle, and then we have all of this sort of conversion-y stuff, and we end up with Kepler's law here, which tells us the orbital period of an object at a specific radius around a specific object. So we can use that to find the mass of stars based on how long it took, so clocks and stuff, and the distance they are from that star or that object. All right. Cool. I think that covers about it.